Hi, welcome. We're going to do the video for 1 through 5. So if you missed any of those, we're going to go through each one. Okay, question number 1 says, suppose the probability of playing softball and getting a hit is 30%. Assume that her chance of getting a hit on a particular time at bat is independent of the other times at bat. What is the probability she will not get a hit until her 4th time? That word until is a big deal. Okay, so I would suggest taking the following notes if you missed this question. Question number 1, you should immediately think that this is a bits or a bins question, meaning it's binary. Either she gets a hit or she doesn't. That's binary. The probability of success here, they gave us, was 0.3, and the probability of failure is 0.7. Now let's think about, it's definitely bits, not bins, because it is binomial. There's a success and a failure. It is independent. They told us to assume that every single time she tries to get a hit, she has an equal chance, and that probability is the same each time. And the T lets us think about that the number of trials is going to keep going until she meets the first success. And that's exactly what it says in the problem. It says she will not get a hit until her 4th time, and then she stops. So we actually have the number of trials it takes until the first success, and the S again reminds us that we need to know the probability of success and the probability of failure, and these should add up to 1. Okay, and that there's nothing in between. So we want to create the fact scenario that the problem describes. So it specifically says the first time at bat she fails again, and the last one she has success. Each of these are and statements. So that means we're going to have to multiply the probability of each one by one another, because I need her to fail the first time and to fail the second and fail the third and to have success the 4th. So that definitely matches number E. They do rearrange the numbers here, but we know the commutative property, I can multiply numbers in any order, so that would match. And if I calculated it, although I don't have to, if I did, it would calculate to that. That's the probability of that outcome. Now, what would be another way to double check our answer? Well, this is in fact a geometric, and that's what bits means. That's the test for a geometric distribution instead of a binomial distribution, which would be bins. So if we put in the probability and we pick when she's going to get her first success, we get exactly the same number, which is another way to double check your answer. Sweet. Next question. What's the probability that this company, or that's the name of the horse, that horse wins the race given good track conditions is 0.6. The probability of good track conditions on any given day is 0.85. What's the probability that the horse wins or the track conditions are good? Okay, so definitely these are asking 2 yes or no questions. So you want to focus on making a table like this. So either the horse is going to win or lose, and either the track conditions are going to be good or they're going to be bad. So those are binomial. There's only 2 choices, good or bad, win or lose. And so what they're saying at the first one is they're saying the probability that he wins, given it's a good condition at the track, is 60%. Well, that would be 60 out of a total of 100. And we set it up like this. At least we know that this is correct. And then we keep trying to figure out if we can find out some more information. They actually give us a little bit more information. They say, in addition to that, you're going to get good days at the track 85% of the time. Now we can fill in some more information here, but I'm not sure that's going to help us. So working through some additional information, if you know, well, I don't know anything more here, but here I know that this would happen 15% of the time. And if I fill in the 60 with this, I kind of know that that would be 25. Okay, so that's the complement rule. Those have to add up. Those have to add up. What I don't know, though, is this number, because if I don't have this information, I can't fill in this and I can't fill in that. So they're asking us, what's the probability that you win? That's you win, adding these two and divide by 100. You win or it's good weather. So that would be adding all three of these numbers and dividing by 100. Well, the problem here is we don't have that number. That number would be if they told us winning and good weather. Winning and bad weather. I wrote that down wrong. So that number is if they told us the probability of you winning and bad weather, it would be that number over 100, but they didn't tell us that. So we have to pick E, that there's just not enough information to process that, and that's our answer. Next question. Sports Illustrated is planning a random sample of athletes asking the question, do you believe in performance-enhancing drugs? And how many athletes would need to be interviewed to provide a plus or minus 2 with a 90% confidence interval? This question, there is an example of this in the book, and this is when we solve for N. We also had one of these on a previous test. So using our formula sheet, and here's my formula sheet, that I think you can find it on there, a 90% confidence interval, and all confidence intervals are created by the statistic plus or minus the margin of error. Our margin of error is our critical value times the standard deviation. So if we look on the chart in the table, this is the number if we're doing a 90% confidence interval. And since nothing is provided in the question, as far as some information we have previous, we have to assume that it's pure indifference, that they're just going to flip a coin and say, yep, I believe it, or no, I don't believe it. So we set P, this is our standard deviation statistic, we set it at 0.5, and the complement of that would be 0.5, and we put it over N, and we're trying to solve for when this margin of error would be less than or equal to 0.2, because that's the plus or minus that I want. Okay, so it's really just an algebra problem. We want to solve for N. So we divide both sides by 1.645. Then we square both sides. So when I divided it, I got that. Then we swap the spots of these locations, and I get this number. So again, we're thinking that N has to be greater than that number, and I can't ask a portion of a person. So the most accurate number, or the fewest number of people you could ask, would be 1692. The number closest to that was D, 1702. Very cool question. Number 4. It says the distribution of grade point averages for a certain college is approximately normal with a mean of 2.5 and a standard deviation of 6. Within which of the following intervals would we expect to find 81.5% of all GPAs? Now this question is a little bit of a tricky one because it's actually from back in Algebra 2. So since we've been doing a lot of confidence intervals, we tend to center the interval on the mean, but that's not what they're asking. So there's a couple ways to solve this question. And I have prepared one way to think about the question. Okay, so if you think about your choices there, our mean is at 2.5 and our standard deviation is 0.6. So they want to know the area under the curve from 0.7 to 3.1. That's the interval provided at A. So if you type that in the calculator, normal CDF, lower bound, upper bound, the mean and the standard deviation, you get 84. I'm trying to get 84.1. So if you do it again, what's the area between 1.3 and 3.7? I get 0.95. Not yet. So once I get to C, I end up getting 1.9 to 3.7, and that's the one that's closest to what I'm looking for. Now you might be thinking, well, that's not 81.5, but they did say approximately. So definitely that's our answer, C. If we keep going, notice these actually get further away from our target. All right? So you might be thinking, well, why did they get 81.5? And I kind of created an alternate solution here. Think algebra 2. There's something really special about all the numbers they produced. So every interval, A, B, and C, and D and E, in fact, were all exactly certain incremental deviations from the mean. So the interval they created on A was exactly -3 standard deviations, and they're asking you to find the area under the curve between -3 standard deviations and 1 standard deviation. On B, they asked for exactly -2 standard deviations to -2 standard deviations, which interestingly enough, this one is centered on the mean. And the 95% rule should have told you that that one's definitely not 81.5. So when you get to C, you notice the standard deviation, just using no calculator, just using this rule, 68% of the data is within 1 standard deviation of the mean. And we know within 2 standard deviations of the mean is 95. So just using the general rule to approximate, we notice that there is 13.5% on either side of there, because there is 27% left to go when I go from 1 standard deviation to 2 standard deviations. When I add the number 68 plus the 13.5, I get exactly 81.5. So that's what they were wanting there. Okay, last question. We'll go real quick. You might want to pause the video. I'll let you see what I wrote down here. And I'll just read this to you. So for question 5, it's very straightforward. To increase power, you definitely want to increase in or increase the significance level.